This is a video for AQA Mechanics, Impulse and Momentum, Section 3.1, Resolving Forces in Impulse Momentum Problems. We've already met the idea that momentum and impulse are vector quantities, so that momentum is mv, and impulse is f times t, or the impulse can be the change in momentum, which is mv minus mu. Remember, when you're writing these, we would normally use underlining, so the bold print for the vectors here would be written mv if we were writing them. In 2 dimensions, we normally use column vectors or I and j, where I and j are the unit vectors in perpendicular directions. Sometimes these will be north and east, but not necessarily. So the column vectors, for example, we might have something like 3i plus 4j is 3, 4. And this is just a rather more convenient way of writing things than using I and j. So let's look at some examples then. Here's the first one where we have a ball of mass 0.5 kilograms is stationary, so initially we have that u is equal to 0 when it's struck with an impulse of 1,5j. So we can say that the impulse is equal to the change in momentum, so mv minus mu, and therefore because u is 0, we can see that v, or at least 0.5 multiplied by v, must be equal to the impulse, which is 1,5, and therefore v is equal to 2 multiplied by that, which is 210. Or in other words, it's 2i plus 10j. Having got the velocity as a vector, we could be asked what the speed is. Of course, the speed then would be equal to the magnitude of v, so the speed is the magnitude of v, which by Pythagoras' theorem would be the square root of 2 squared plus 10 squared. So equal to the square root of 104 in this case. In the second example, we have something which is initially moving with a velocity of 3 minus 2. So this is u written in its ij form, and the impulse again is 1,5. So we can say that the impulse I is mv minus mu, and that gives us that the vector 1,5 is equal to 0.5 multiplied by v that we're trying to find, minus 0.5 multiplied by the initial velocity 3, negative 2. So if we multiply up by 2 and then add the initial momentum to the left hand side, we get that the v is equal to 2 multiplied by 1,5 and then plus 3 and negative 2. That gives us a value of 5 on the top line and 8 on the bottom, so a value of 5,8, which is 5i plus 8j. Next part of the question says, once we've got that velocity, which was 5i plus 8j, asks us to work out the speed and the kinetic energy of this. So the speed is equal to the magnitude of the velocity, which is the square root of 5 squared plus 8 squared, and that comes to be the square root then of 25 plus 64, so that's 89, square root of 89 meters per second. The kinetic energy is equal to 1/2 mv squared. So we know that v squared is 89, so this is 1/2 multiplied by the mass 0.5 multiplied by 89. So that's 89 over 4 in total, or a value of 22.25 joules. In this example, we've got a mass of 2 kilograms, which is travelling in the direction 3I plus 4j and a speed of 1 meter per second. It's then acted on by a force of 4 newtons in the I direction for half a second, and we're asked to find the velocity of the particle immediately after the force has acted. So let's consider the initial velocity first of all. If it's travelling in a direction of 3, 4, then we can see that that would give us a hypotenuse equal to 5, 3.345 triangle there. So if we want a velocity of, or at least a speed of 1 meter per second, then we would have to have not the vector 3, 4, but here 1/5 of that. So the initial speed is 1, means that the initial velocity must be 1/5 of 3, 4, which is then 0.6, 0.8. The impulse F is given by force multiplied by time, so the impulse I is equal to the force F multiplied by time. The force is equal to 4 newtons in the I direction, so that's 4 and 0, multiplied by time of 0.5. So the impulse is equal to 0. So we can now use that the impulse I is equal to the change in momentum mv minus mu, and substituting what we now know, we've got the impulse 0 is equal to 2 multiplied by the velocity that we're trying to find minus 2 multiplied by the initial velocity, which is 0.6, 0.8. Dividing through by 2 and then adding gives us that v is equal to 1 plus 0.6, so that's 1.6, and plus 0.8. So it's 1.6 I plus 0.8 j. This final example, very similar to the last one, but this time you'll see that the initial velocity is given as a speed 0.5 at an angle of 30 degrees to the initial direction. We've got a force, this time magnitude 2 newtons, acting along in the I direction, and for 1 second. So we can say that the impulse I is equal to force multiplied by time. So the impulse is equal to a value of just 2I. Impulse is change of momentum, so impulse is mv minus mu. So we can say that 2 multiplied, the impulse rather, which is 2I, is equal to the mass 2v minus 2 multiplied by the initial velocity, which I need to get into component form. So we've got 0.5 cosine of 30 degrees in the I direction and 0.5 sine of 30 degrees in the j direction. And if you rearrange that, calculate, we get that v is equal to 0.933 I plus 0.25 j. Well, that concludes this video. In the next one, section 3.2, we'll look at oblique impacts of objects on fixed surfaces.